All right, guys, let's go ahead and begin. Welcome to Advanced Quant. And I want you to look at that tagline very carefully. The tagline says, why are we doing these? And that's actually kind of a valid question. So I want you to really consider, why are we doing these? Because in my opinion, they're not super valuable. Anyone, why do I think that? Anyone have an idea? Why are these not that valuable? John, how are you, John? You have to unmute your microphone.
I'm doing okay. Thanks for having me.
Hey, no problem. So why are these not that valuable? What do you think?
Because there are not that many of them on the test.
Well, I would say there's 0 of them. So a lot of the problems you're going to see today are GMAT problems because GMAT math is harder. So in terms of the actual GRE, you might see one of these, maybe, but probably not. Yeah. So I guess my question is, why are you guys so interested in doing these? Anyone want to raise their hand and kind of give their opinion? All right, let's go to Yi Do. I don't know if I'm saying that right.
Hey, Greg. Yeah, you're saying it right.
Cool.
Hello, can you hear me?
Yeah, I can hear you. Yeah, you're clear.
Okay. I think we want to do advanced questions because we think that by mastering these, we'll be able to do the questions that are lower difficulties.
Yeah, I guess it's possible. Yeah, definitely. Okay, thank you for your opinion. I guess I don't know, do we have any baseball fans in here? So on baseball, in baseball, there's something called the home run derby. I'm not sure if you guys are familiar with it. So in the home run derby, here, I'll spell it for you guys. In the home run derby, basically the goal is to hit as many home runs as possible. And the pitchers, the people who throw the ball, they throw only fastballs. And the reason why this is valuable is because a fastball is straight. And if the batter knows a fastball is coming, it's predictable and they can hit it as far as they want. So I guess my question is, what is the value of practicing curveballs? And a curveball is a ball that, curves, that's why they call it a curveball. What's the value of practicing a curveball if we're going to be participating in the home run derby? And I'm not saying there's no value to it. I'm just saying it's something to think about, some kind of debate that I guess we can have. But I know you guys are interested in doing these, and I enjoy doing them as well. If you want my own theory, I think the reason why we like doing these is just because they're fun. I think they're fun. They're like little puzzles. All right, so let us move on here, and let's do some advanced quant. Are you guys ready? Dun dun dun. Here we go. All right, so whenever people come across an advanced quant question, I've kind of noticed a phenomenon. And the phenomenon is basically the person will stare at the screen and then kind of do nothing. And of course, this is bad for 2 reasons. Not only are you probably going to get the answer wrong, but you're also wasting precious time that could be applied to some other questions. So if you do come across one of these really difficult problems on the GRE, or what you perceive to be one of these really difficult problems, it is imperative that you move on after about 30 seconds or a minute if you cannot figure out what exactly is going on. Because if you're going to sit here for like 4 to 5 minutes, not only are you probably going to get it wrong, because these questions shouldn't take 4 to 5 minutes to solve if you know how to do them. So not only are you probably going to get it wrong, but like I said, you just wasted 4 to 5 minutes that could be applied to other questions. So with that caveat in mind, or caveats in mind, we can continue. So this is almost like my disclaimer to you guys, because we're about to see some questions that might make you feel frustrated, or that might be more difficult than you imagined. But of course, the name of this course is called the Advanced Quant section. And if you are interested in finding some of these problems yourself, again, my recommendation would be the GMAT. The GMAT does have a higher caliber math question, but kind of a lower caliber verbal question, in my opinion. So the GRE verbal is a little bit tougher, and the GMAT math is a little bit tougher. All right, with that said, here we go. Okay, So when we say a tough question, I think what you guys really mean is legitimately a tough question. So I wanted to give you an example of a hard question, but not hard because it's difficult, hard because it's tricky, or hard because it's easy to fall into a trap. And so I thought this was a perfect example. And I only have a couple of these, but I want to kind of, show you guys there's a dichotomy here. So questions can be difficult because they're legitimately hard and they test a variety of concepts, but a question can also be difficult just because it's tricky and you can fall into a trap. This would be an example of the second one we just talked about. So go ahead and take about 2 minutes and see if you can solve this problem. But even more importantly, can you identify what the trap is or what the trap answer is? All right, I'll give you guys 2 minutes. All right, guys, that should be enough time. So on the surface, this is an easy problem. And whenever something is an easy problem on the surface, you have to be kind of careful because the GRE can really throw a curveball at you. So basically, the trap is this. The trap is, okay, so the probability that he mows the lawn of one of these neighbors each day is 1/5. Well, if he's going to mow the same lawn in 2 different days or back-to-back days, well, then I'm just going to do 1/5 times 1/5. Correct answer is 1/25. Unfortunately, this is wrong. This is not the correct answer. And the reason is because I don't care which neighbor we're talking about. This is only one neighbor, the case of one neighbor, like Bob, for example. So the first probability is not 1/5. The first probability is who cares? It could be any house. I don't care. It could be Bob. It could be Sarah. It could be Melissa. It could be, blah, blah. It doesn't matter. So the probability of the first choice is actually 5/5. And the probability of the second choice is something that we care about because it has to be the same one as the one we just chose. So for example, Bob. So in that case, it would be 1/5. So in this case, the probability is basically 1 times 1/5, which equals 1/5, like that. So as you can see, it's not a very difficult problem, but it is kind of a tricky problem or a problem with a trap that people can easily fall into. All right, so that's one example of one of those. We're going to look at another example here pretty quickly, but any questions about this one? Deepasha?
Yeah, hi, Greg.
Hey, how are you?
Yeah, I'm good. I had a different approach to solve this question. Please tell me if that is the correct one because somehow I got the correct answer.
Sure.
So, what I did, the total number of options would be 5 combination 1, combination of 5 to 1, so which would be 5.
Correct.
And then what I did, like first one would be for only one house, so that let's take that as 1. And what I did for the whole 5 days, I took the only one option, like 1 into 1 into 1. So 5 times. And what I did, I divided that into 5 combination of 5 1. Was that correct? So what I did, instead of back-to-back days, instead of 2 days, I did it for 5 days and all with only one option.
Yeah, I guess that's certainly not how I would do it. Another way that I would do it is I would look at the 5 neighbors like this. So we have Bob, John, Sarah, Melissa, and Frank. And then for each one of these, the probability that I mow their house in back to back days is going to be 1/25. So all the way down. So you have 5 people. And so it would be 5 times 1/25. So that would be the alternate approach that I would take. The approach you took, I'm not saying it's wrong, but that certainly wouldn't be what I would do. But to me, that seems like needlessly complicating things.
Yeah, I guess I took it for all 5 days instead of 2 days.
Yeah.
And might be because of that, I got somehow correct answer, but that's not the correct approach, I guess.
I'm not ready to say it's not the correct approach. But I can tell you definitively that's not how I would do it.
Okay,
Cool.
okay.
Makes
Thank
sense?
you.
Okay.
Yeah, thank
All
you.
right. Zial, you got a question?
I cannot understand the answer. How you solve this?
So basically, and I don't want to spend too much time here, basically, the first choice doesn't matter. I could choose Bob, I could choose Jessica, Samantha, Melissa, or Frank. It doesn't matter. Really, the second choice is the only thing that matters. So if the first choice doesn't matter, the probability is just 1. And then the second choice, I have to be the same as the house before. Well, that means it has to be 1/5. And so really, it's just 1/5. And again, this is actually an example of an easy problem, in my opinion, that's just tricky in terms of the way it's structured. We're actually going to be looking at some pretty hard problems here pretty soon. So I don't want to spend too much time on this problem. Here's another problem, which again is not very hard, but is tricky. Okay, go ahead and I'll give you 3 minutes to do this one. All right, 3 minutes. Okay, go ahead. Okay, give you guys about 1 more minute. 1 more minute. All right, guys, does anyone want to raise their hand? And I'm not that interested in the answer. I'm more interested in the trap or the trick. So what exactly is the trick here where they're trying to get you? It's almost like a reading problem. Heather?
I think the trap is that the time on the treadmill is the time remaining.
Exactly.
Not,
So it's
yeah,
actually going down.
yeah.
There's the trap. So it's actually a reading problem. Good job, Heather. That's exactly correct. It's not the time ticking up, it's the time going down. And so, again, notice it's not an overly hard problem if you kind of understand what it means from a reading point of view. So, what that means is when she has 10% of her exercise session completed, she has 90% remaining right there. And then the 90% remaining has to equal this time right here, which is going to be 24 minutes and 18 seconds. And of course, you can just find out, basically 0.90 total. That's going to equal 24 minutes and 18 seconds, like that. That will give you the total. And then finally, when she's completed 40% of her exercise session, she'll have 60% remaining right here. And then you just take 60% of the total, 0.60 of the total, and the answer you get is E right here. So once you actually figure out how it works, again, not a very hard problem. So that's what I wanted to show you guys. The first two, not overly hard problems, but they are tricky, they are trappy. You do have to understand what they're asking you and things of that nature. But we're about to see some actual legitimately hard problems. And I'm not trying to scare you. I'm just trying to kind of, like I said, show you this dichotomy between, a problem can be hard because it's tricky, it's trappy, or a problem can just be hard. And we're about to see some of these hard ones. So before we do that, any questions? All right, Heather?
Yeah. So how would you normally deal with this whole issue of seconds?
I put everything into seconds. It's a good
Okay.
question. Yeah. So what I'll do is I'll just do 24 times 60 and I'll just add the 18, for example.
Okay.
Yeah. Yeah. So if you ever have mixed units, just put it into one unit.
Okay. Yeah, that's way easier than what I did, was try to work out what the decimal of a minute was 18 seconds. And
Well, you did actually try to put it into one unit, so that's good. You just did kind of the harder way, because if
Okay.
you put everything into seconds, it guarantees that you're dealing with integers.
Okay.
Yeah. Okay. Good question. All right. Any more question, guys? All right. Are we ready? Oh, Johnny. Johnny has a question. Hey, Johnny, how are you?
Hey, Greg. Can you just go ahead and explain this question again? Because I kind of got confused with it.
Sure. So at the fourth set, or at the beginning, I want to just say it's a reading question. Okay, just keep that in mind. So when she's completed 10% of her exercise session, how much does she have left? What percentage does she have remaining?
90.
90%. So if you figure that out, you figured out the problem. See, a lot of people, what they're going to do is they're going to start saying, okay, so 10% of the 24 minutes, 18 seconds, and they're going to do that math, and it's going to get them nowhere. They're just going to go in the complete wrong direction. But if you realize that she has 90% remaining, well, look, they gave you the remaining time, right? They told you what the remaining time is, 24 minutes and 18 seconds. So 90% of the total, that's a variable right there, has to equal 24 minutes and 18 seconds. And then once you find the total, it's pretty straightforward from here, because if she's completed 40% of her workout, how much does she have left? What percentage? Johnny, you there? Oh, Johnny muted his mic. Okay, so the Dara, DARA, has 60% remaining on her exercise. And you know what that means? It just means 60% of the total time. We already calculated the total time right here. And so the correct answer is going to be E right there. So I just kind of spared you guys the math. Nitin, question?
Hi, I think I got lucky. I used 24.18. And then
So
I
yeah, that would be
divided by,
lucky, because
yeah,
18 over 60 is not 0.18.
Yeah. I
Yeah, so
divided by 0.9 and then multiplied by 0.6, and then I got the exact answer.
yeah, you got lucky. Yeah.
Yeah.
Probably what happened is your mistakes canceled out.
Okay.
Yeah. Okay. Cool. All right. Let's move on to like what I would consider a legitimately hard problem. Again, we're not trying to intimidate anybody. If you find these problems hard, they're supposed to be. Okay. So just keep that in mind. And here it is. N is the smallest multiple of 20, such that n squared is a perfect cube and n cubed is a perfect square. How many digits does n have? And I actually solved this problem in a recent video of mine. Okay, so before I solve it again, I want you guys to give this a shot. And I chose this problem specifically, not because I don't have a wide collection of hard problems, but because this problem very kind of clearly illustrates a technique and a process that you have to follow when you do difficult problems. So before I show you what that process is, how about you guys take 3 minutes and see if you can figure this one out? Okay, go ahead. Okay, everyone, that is 3 minutes right there. Now, obviously, if this was the real GRE, you probably wouldn't even see this problem. But even if you did, you should probably have skipped it by now if you didn't figure it out. If you find yourself still kind of staring at this problem, 3 minutes later, that in itself is a big problem. So now that we talked about staring, let's talk about staring. So whenever a problem is very difficult, the kind of 1,000-mile stare is very common. That kind of shell-shocked look that was very common in World War I. And what you have to do is you just have to do something. So that's why this problem is so good, because it really illustrates this idea of just doing something, even if it's wrong. Okay. And that's number one. Number two, you have to break the problem into parts. Break it into parts. So I'm actually going to show you how this works if you haven't seen the video. So it says n is the smallest multiple of 20. Stop. The smallest multiple of 20 is 20. Okay, so I say, all right, n is 20. See how I'm already doing something? I'm already breaking it into parts here, such that n squared, okay, so if n is 20, n squared is going to be 400. Is a perfect cube. Uh-oh, problem. 400 is not a perfect cube. Now, how do I even know 400 is not a perfect cube? Well, basically, because if you say x3 equals 400, x is not an integer. It's a number with a decimal on it. And then maybe if you want to put it in more math terms, is that 400 to the 1/3 power does not equal an integer. You have some decimal stuff going on here. So I know that my first n value didn't work here. Okay, that didn't work. All right, so what do I do now? Well, these numbers are getting really big. So how about I break n into its prime factors? So I say, okay, if m has to be a multiple of 20, that means it must contain inside of it, it must have a 2 and another 2 and a 5. Okay, so now I'm getting somewhere. So if I write it like this, it's going to be 2 squared 5 to the first. And then if I say n squared, well, then n squared is going to be 2 to the fourth and then 5 to the second. Again, notice this doesn't work, because if I do 1/3, if I put a 1/3 here, what I'm going to end up with is 2 to the 4/3 and 5 to the 2/3. And notice this is a decimal. So I want these things right here to be integers. Right now they're fractions. Well, how do I make them integers? I have to make these right here multiples of 3. So my new n value is going to be 2 to the 3 and then 5 to the 3. And notice what happens when I do n squared. When I do n squared, I get 2 to the 6th, 5 to the 6th. And if I take 2 to the 6th and 5 to the 6th, and multiply that by 1/3, or raise it to the 1/3 power, I get 2 to the 2 and then 5 to the 2, which is not a decimal. This is an integer. And I'm like, I'm done. The correct answer is n must be this right here. N equals 2 to the 3rd and 5 to the 3rd. But then we run into a problem with this bad boy right here. Okay? So imagine this is my n value. This n value works with n squared. No problem. The problem is when you take n cubed, okay, that's going to be 2 to the 9th and 5 to the 9th. Is that a perfect square? The answer is no. For this to be a perfect square, these two numbers have to be even. And notice they're both odd. So my original n value doesn't work. So now I know the n has to be a multiple of 3 on the exponents. And then finally, I know it has to be even as well. So notice this is a multiple of 3, this is a multiple of 3 right here, but it's not even. So the next logical choice is going to be 6. 6 is a multiple of 3, and at the same time, it is even. So the final answer is going to be 2 to the 6, 5 to the 6. But there's still one more step to this problem. How many digits does n have? Well, what number is this? This actually equals 10 to the 6, which equals 1 million. 1, 2, 3. And then finally count the number of digits. 1, 2, 3, 4, 5, 6, 7. Final answer is 7. Now, I'm not saying this is an easy problem. It's not an easy problem at all. It's a very difficult problem, but it's even more difficult if you just stare at your screen and do nothing. So I want you to really kind of look at my process here. I started with 20. I realized it didn't work. But in realizing that it didn't work, I kind of figured out what was going on here. I'm like, okay, I need this to be blah, 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 a multiple of 3. And then finally, the multiple of 3 didn't work, and I had to throw in that even exponent as well, which allowed me to land on the correct answer right here. N equals 2 to the 6th, 5 to the 6th. All right, any questions about this? Samuel.
Hey, how's it going?
Good, how are you?
I was just wondering how we established that 2 to the 3, 5 to the 3 is a multiple of 20. Just
Good
right
question. So remember, 20, that's a good question, by the way. 20 has a 2, a 2, and a 5, right?
Right.
So all I need to be a multiple of 20 is 2 2s and a 5, right? So if you look at 2 to the third and 5 to the third, do I have 2 2s and a 5?
I suppose we do.
Yeah, so that's why. Yeah. So basically, you can always determine if something is a multiple of something if they have the same components. So I only need 2 2s and 1 5. Well, I actually have 3 2s and I have 3 5s. So it works out. Cool.
I see. Well, thank you.
Yep. Good question. That's a very good question, by the way. Iqbal John, question.
Hello.
Hey, how are you?
I'm good. How are you doing?
Pretty good.
So how did you end up getting the multiple? I mean, how did you understand that we're going to need to use not the multiple, but prime factored form of 20? Because what I kind of worked with just 20 itself, and they ended up getting 20 to the sixes.
Yeah, I guess you could, but for me, whenever I deal with these large numbers, I just find it much easier to deal with the prime factors.
And that what exactly kind of pushed you to choose the prime number?
Habit. So anytime I'm dealing with prime factors, or anytime I'm dealing with factors or squared or perfect cubed, I always just break it down into prime factors. Some problems really require it, so it's almost like a force of habit. If you want to use 20 here, that's probably okay, because if you start with 20 to the, actually no, it's not going to work.
No, it's not going to work.
Yeah, no. So you do have to break it down into prime factors. So for example, if you say 20 to the 6, it's not going to work. Yeah.
Yeah, so because in your case you're using a factor of 20 only one time,
Exactly.
like 2 to 6 is, and I'm using it like 2 times.
Yeah, you kind of have extra numbers in there that you don't need. Notice it
Yeah.
says the smallest
Small.
multiple right there. So yeah,
Yeah.
actually you do need to break this down into the prime factors. Good question. Good question.
Okay. Thank
Okay.
you.
All right, so that's the process, guys. You basically have to do something. All right. And if you're solving these at home because you like the puzzle, and you're not worried about the time, then my advice would be, spend 10, 15 minutes with one of these questions until you can figure out what's really going on. All right, let's look at another one here. Okay, so this one says, Chris, our friendly neighbor from the previous question, drives from his home to his job each day. Because he's crazy, he allows himself to only move north or east. How many different routes to his job are possible? Okay, guys, I'll give you 4 minutes for this one. I see a lot of you guys saying that these problems are hard, but just let me remind you, it's called advanced quant. So I'm not trying to scare anybody. I'm just kind of conforming to the title of the class. All right, everybody. That's 4 minutes. So this is a hard problem. It's not an easy problem. But kind of following our ethos here to just do something, can somebody raise their hand and tell me what is something I can do? There has to be one thing I can do here, just so I'm not staring at the screen. Samuel, what do you think?
I kind of feel like every side of sort of an element in the grid represents a different path that could be taken with north or east. So I think it's maybe just 12 times 4.
So you're trying to get the final answer rather than just kind of starting, basically.
Sure.
So if you try to kind of jump to the finish line, it's probably not going to work. Let's see.
Makes
Equal
sense.
John, what is something that I can do? Just like step 1.
I would say you would just start counting different approaches. Like you would go from like to the farthest east, and then
How about just one approach? So like, see, notice you guys are saying like approaches. How about just one? Right? Let's just find one successful route. Okay. Let's just try it. Let's just see what happens. So for example, I go up like this, right? Okay. So I start by going north. All right. And then I go up again. And so I go north again. And then I go up again and I go north again. And then I go up again and I go north for the last time. And then no choice, I have to go east, east, and then east. Okay, so this right here is one successful route. All right, interesting. Let's try kind of the opposite route, right? So then I go east. All right, so then I go east. And then I go east, and then I go east. And then I go east for the final time, and then I go east. And then no choice, I have to go north how many times?
4.
4 times. Huh, interesting. What do you notice about these 2 examples that we just came up with?
Like 3 easts and 4 norths?
Yes. So no matter what route we take, it doesn't matter. We have to go 4 norths and 3 easts. 3 easts and 4 norths. Don't believe me? You can even go in the middle. North, east, north, east, north, east, north. So here's another example. North, east, north, east, north, east, north. So no matter what we do, we have 4 norths and 3 easts, which allows us to solve this problem. Think about it like a word, right? If you have the word egg, how many different ways can you rearrange this word? Well, there's actually a formula. You take the total number of letters, which is 3 factorial, and then you remove the repeats. So notice this has 2 G's here. So you can just say 2 factorial, final answer is 3. Same thing here. It's just a formula, okay? It's not rocket science. It's not like I figured this out on my own. So we have a total of 7 letters, so 7 factorial. We have 4 N's, so 4 repeats, and we have 3 E's, so 3 factorial, and then finally we can solve this. So the 4 is going to cancel with most of the 7. So we have 7 times 6 times 5, and then 3 times 2, which is 3 factorial is 6. So notice that the 2 6's cancel right here, and you're left with the final answer of 35. And the reason we were able to get this answer is because we just started small. We just said, okay, let's look at one successful case, and then let's look at another successful case. Are we noticing any kind of a pattern here? And then once you notice the pattern, you can actually figure out this pretty difficult problem. Okay, any questions about this one?
Here, can I ask?
Sure, go ahead.
I tried to find a pattern by just going north, 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 and then east, east, east. That gave me one option.
Mm-hmm.
And then I went like north, 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 then east, and then north.
So you weren't trying to find a pattern, you were trying to brute force it. And
Yeah,
brute
well,
force it means you were trying to find all possibilities, right?
Yeah, so in the first case, it gave me one answer. In the second route, it gave me 3, then 6, then 9, and I was like,
Yeah. So you were
going
trying to
on.
brute force it. And if you're trying to brute force something, you're not really trying to find a pattern, are you?
Well, I kind of found it.
Not
1,
really.
3,
Not
9.
really. If you're trying to count the number of routes that way, you're actually trying to kind of do it by exhaustion. And that is a possibility. You can do it that way, but the problem is it's going to get very kind of complex, right? And it's easy to make a mistake. So notice my 2 successful routes. My second route was not a slight adjustment on my first route. It was a completely different one, all the way at the bottom. Make sense?
Okay.
Yeah.
Thanks.
Okay. Good question. All right. Any questions? Let's go with Rahul. Hello, Rahul.
Hi, Greg. How are you?
Pretty good.
Like, how did you know that 7 factorial by 4 factorial into 3 factorial is the number of ways possible?
Because that's the number of ways to arrange this word. So this word has to have 4 N's and it has to have 3 E's, right? So how many different ways can I arrange that word?
Okay.
Make sense?
Yeah, got it. Great. Thanks.
Deepasha, question?
Yeah, I was trying to find out any different pattern here. So one pattern which I found, there are 3 N's and 4 E's. But anyways, in that case also we have to divide it by 4 and 3 because that is a repetition, right?
Correct. Yeah, that's kind of what we did here. Yeah.
Yeah, and one more question, please correct me. So if, as they have asked here, how many different routes to his job are possible, that's the reason why we are canceling the repetitions, right?
Exactly correct. Yeah, because if you do it like this, if you do 7 times 6 times 5 times 4 times 3 times 2 times 1, you're including a lot of repetition in there.
Yeah. Okay, I got it.
Make
Thank
sense?
you. Yeah.
All right, let's move on to another one. Okay, guys, try this one. If x is the smallest positive integer that is not prime and not a factor of 50, what is the sum of the factors of x? And again, I'm going to give you a piece of advice here. Start small, even if it's wrong. So start with the most obvious answer, even if it's wrong. Okay? Because that will allow you to kind of figure out what's going on in the problem. All right, I'll give you guys 4 minutes for this one. Okay, one more minute. Okay, that is 4 minutes here. And let's actually do this one together so you guys can raise your hand. But I don't want you to tell me the final answer. I want you to do this very piecemeal. So I want you to imagine I don't know what the hell's going on. Right? What the hell? Okay. What would be step one? All right, Marin, what do you think?
Hi, Greg. I think the step one would be to find the smallest integer, that is to find x. So if something has to be not a factor of 50 factorial, then I would first take it as something just above 50 factorial. So I would take it as 1.
Yes, exactly. So her mic wasn't that clear. So if you didn't hear her, that's exactly correct. So what you do, remember, 50 factorial is going to be 50 times 49 times 48, dot, 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 all the way to 3 times 2 times 1, right? And so what Marin said was actually genius. So she knows that the numbers 1 to 50 are all going to be factors of this 50 factorial, of course, right? Because it's 50 all the way to 1. So logically, you should just say that x equals 51. Just start at the beginning, even if it's wrong. Okay, so x equals 51. Now the question becomes, is this a prime number? Because remember, it's supposed to say not prime. Well, no, 51 is not prime, and I know it's not because 5 plus 1 equals 6, indicating that it is a multiple of 3. Okay. Number two, the question is this a factor of 50 factorial? Now, on the surface, it's not, but you need to analyze it a little bit more deeply. How do you make a 51? You make a 51 with a 3 and a 17. Do I have a 3? Damn right I got a 3. Do I got a 17? Damn right I got a 17. 3 times 17. So that is a factor of 50 factorial. But at least I'm starting to figure out how this problem works. I'm like, oh, okay. So the x value has to be something that's actually bigger than 50 factorial. And the question is, how much bigger? How much bigger is the question? So what you can do is you can try another number like 52 and you say, hey, can I make a 52? Obviously, it's not prime. Well, yeah, because to make a 52, all I need is a 26 and a 2. I got a 26 and I got a 2. All right, let's go even bigger. Can I make an 80? Sure. All I need is a 4 and a 20. I got both of those things. Can I make a 100? Sure. All I need is a 2 and a 50. And then you go, okay, can I make a 101? Well, 101, I believe, is going to be a prime number. Remember, they say not prime, okay? So it can't be 101, okay? That doesn't work. Can I make a 102? Well, that's going to be 3 times what? Okay, what is that? So it's going to be what? 3, so 33, 34, right there. You have a 3 and you have a 34. So, but you're getting close. You're getting close, okay? If you go to 106, how do you make a 106? You have to make it with a 2 and a 53. See this bad boy right here? This bad boy is prime, and it is not part of 50 factorial. So I found my x value. The x has to be 106. But that's not the question, is it? The question is, what is the sum of the factors of x? Well, 106, what are the factors of 106? Well, clearly 1 and 106, and then finally 2 and 53. And if you add all of these together, 106, 53, 2, and 1, The correct answer is 162, right there. And so Marin was very smart by starting with 51 because it allowed us to crack this problem. It allowed us to crack it and kind of figure out what exactly is going on. Okay, any questions about this one? All right, Rahul?
Like, can you explain the part where we have to start from 51 again, Greg?
So basically, you have to do something, right? And so the x value cannot be a factor of 50 factorial, right? So logically, the place you should start is just say that x, the factor is 51. Because 51 is greater than 50, right? Because obviously 1 to 50 are going to be a factor of 50 factorial, right?
Yeah.
1's a factor, 2's a factor. So the logical starting place is probably going to be 51 here. Does that make sense?
Yes. Got
Okay.
it.
No, it's not the correct answer, but it's definitely a logical starting place. Okay. Abdullah, question?
Hey, Greg. When you wrote 106, you wrote 2 to the 53. 53 is a prime.
Correct. Yeah.
So I'm just confused that 2 is also a factor of 50 factorial, right?
Correct.
So why did you take that 106?
Because, well, first of all, 2 is a factor, but 53 is not, right?
Mm-hmm.
So both of these have to be factors in order to be inside here. Don't you agree?
Okay,
you
so
have to have a
both need
2. Yeah, you have to have a 2 and a 53.
Okay. So the reason why you canceled x equal to 51 because 3 and 17 both were in 50 factorial.
Exactly, 100%.
Okay, so
and that's the same reason why I canceled 102. So inside 102, you have a 3 and a 34, right? I have both of those in 50 factorial.
Yeah, so 5 and so 53 is a prime, but the question says it's not a prime.
Yeah, so 53 would be a logical x value, but the problem is they say it has to be not a prime. See where it says not prime?
Yes.
So 53 actually works, but it violates rule number 1.
Yeah.
Okay, makes sense? So for example,
okay.
106, is 106 a prime number?
Yes, it is prime.
No, any
no,
even
no,
number.
It's not prime.
It's not prime,
No,
right?
no,
so
it's not prime.
that means
divided by 2.
Yeah, exactly. Okay. And so 106 is not prime, and it's also not a factor of 50 factorial, which means it is the smallest positive integer that is not prime and not a factor of 50 factorial.
Okay, so you just started like with 51, you just came on going, and then eventually you just came up factorizing a number and realizing that, hey, these two factors are not in 50 factorial, so boom, that must have been the answer.
Yeah, and eventually what you're going to realize is in order for this to be the correct answer, you have to have a prime factor that's bigger than 50 factorial. And the smallest prime number bigger than 50 factorial is going to be 53, right? That means 53 must be inside the x answer. So if you want to take a shortcut, you know that the smallest integer that's not a factor of 50 factorial and not a prime, if you want to take a shortcut, it has to contain a 53. It can't be 53 itself because 53 is prime, and that violates one of the rules. So the next smallest multiple of 53 is going to be 53
times 2.
Exactly. So 106.
Yo, that's genius. Thanks, man. Thanks.
Yeah, makes sense. Okay, good question. Yeah. All right, we got a lot of questions here. Let's see. Next one, D. Pasha.
Yeah, Greg. Yeah, I had the same question. How did you, for the first approach, I was correct. My approach was correct. Like, should be a number which is not coming from 1 to 50. But when it is coming to that one, when you jumped from 52 to 106, so I was about to ask the same question, how to find out, like, do we need to find out that the number should be should contain a factor which is greater than 50. So
yeah,
you just
and
answered
specifically, it should contain the smallest prime number that's bigger than 50.
Yeah, I just answered that. Thank you.
Okay, good question. Marin, you started us off. You got a question?
Yes, I do. Actually, I might have got the first part right, but the answer was wrong. So basically, when I took 51, I thought 51 into 50 factorial divided by 50 factorial. So the 50 factorial gets cancelled, and then therefore 51 is not a factor of 51.
Yeah, I think you just misunderstood. So the question is, with 51, can you make that number out of 50 factorial? And the answer is yes, you can, because you're going to borrow the 3 and borrow the 17. Okay.
Thank you.
Makes sense. All right, let's see. Kshama. I don't know if I'm saying that right. Kshama. Are you there?
Yeah.
How do you say your
I
name?
just it's Shama.
Okay, Shama.
I just wanted to know if we need to practice these kind of questions a lot.
No,
Or
I told you at the very beginning. I said, why do you guys want to do these? Yeah, these kind of problems don't come up on the GRE. Now, if you enjoy doing these, sure. But if you're getting scared by this class, that's not the intent of the class. Okay, so I'm not trying to scare anybody here, right? We're just doing this because I'm trying to stay true to the name of advanced quant. Does that make sense?
Okay, thank you.
Okay. Iqbal John, question?
Hello.
Yep, hey.
So you came up with 106. So until then, you kind of tried.
No, I did that just for illustrative purposes. I knew that it had to contain the smallest prime number greater than 50, and I knew that I couldn't use 53 by itself because that's a prime number, so I just did 53 times 2.
Oh, okay.
So when I
But
solved this problem, I just took the shortcut.
okay. So, but what if we are kind of trying several numbers, like picking a number, when we actually have to stop?
Well, obviously, you have to watch the clock. And remember, when you're choosing these multiple numbers, you're going to be trying to look for a pattern. So you're going to be like, okay, well, wait a minute, 100 doesn't work because I just need the 50 and the 2. Oh, so I notice the number that I need here has to be bigger than one of these 50s. And you go, oh, I need the 53. Boom, like that.
Oh, okay. So yeah, so because until 50, it is factorial. I mean,
Mhm.
it is within the factorial of 50, right?
Right, exactly. So you
Oh,
need a number bigger than 50. Exactly.
all right. Thank you very much.
Okay. All right, guys, let's do one more question, like a bonus question. All right, here you guys go. I'll give you 3 minutes. All right, about one more minute.
20.
All right, guys. So I'm just going to walk through this with you here. So this is another good example of where you should just start with something. So let's imagine, because remember, we have letters. We have 6 letters. So we have letter, 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 letter. And then we have, what, 4 digits? So D, 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 D. Let's imagine that we're going to choose these in order. Let's just imagine that. No choice. So we have to choose a letter. We have to choose a letter. We have to choose a letter, and a digit, and a digit. Notice the problem doesn't say that it has to be in order. You know, you could be like digit, digit, letter, 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 or a digit, letter, digit. It doesn't matter. But let's imagine that it does matter and that we have no choice. We have to follow this order. Well, this is just a choices problem, isn't it? 1, 2, 3, 4, 5, 6. How many choices do I have? Well, for the first one, I have 6 letters, so I have 6 choices. And then remember, they have to be different, so I can't do 6 choices again. All right, so the next choice is going to be 5, and then 4, and then 3. And then I've already kind of exhausted all of my letter choices here. So for the digits, how many choices do I have? Well, how many digits do I have? 4. So I have 4 choices here and then 3 choices here. And of course, that's going to be all multiplied together. But remember, these can move around. So this should kind of bring you back to our north, 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 east, east, whatever problem. How many different ways can you rearrange the letters in this word? Well, you can do, okay, 6 factorial, because you have 6 things here. And then 4 of them are repeats, 4 letters, and then 2 digits. And this is going to equal 6 times 5 over 2, which is going to equal 15. So this is one example, one successful case right here. And then you have 15 total cases. So what you do is you multiply this by 15. So final answer is going to be 6 times 5 times 4 times 3 times 4 times 3 times 15. Let's see if we can do this math. So we have 30. So 4 times 4 is 16 times 6. Oh, sorry, times 9. Let's go ahead and do this. 16 times 9 is going to be 160 minus 16, 144. Is that right? So 30 times 144. I think that's correct. I'm doing it in my head. Could be wrong. All right, then I'm going to get out my phone calculator. 30 times 144 is going to be 4,320. And then finally, don't forget this last thing right here, times that by 15, and that's going to equal 64,800. So here's the correct answer, everybody. And the key part here is I just started with one example, and then I kind of said, hey, how many different ways can I do that? And it's 15. All right, so before I call it a night, any questions about this one? Surya, hello.
Hi, Greg. So I got the first part correct, 4320.
Mm-hmm.
And the other thing was, what is a 6 factorial by 4 factorial by 2? 6 factorial by 4 factorial into 2 factorial.
This is the different ways to arrange these letters. So for example, you could have DL, L, D, L, L, for example. There's 15 different ways to arrange the letters like that.
Oh, okay. But it's given in the question that if any given code or character, they did not mention, right? It can be jumbled or something. I just
but they don't mention that they have to go in order. So that means by default they can be jumbled.
Okay.
Yeah, makes sense?
Yeah. Got it.
Okay, guys. Hey, I have to call it a night because my dog is acting a little bit crazy. But if you guys have any questions, you can just message me on Discord, and I'll have this up as a recorded lesson tonight. I'll put it up pretty soon. Somebody was requesting that. Like I said, so this is advanced quant. I think the main takeaway here, everybody, is just do something, even if it's wrong and even if it's simple, because kind of in doing something you can maybe figure out how the problem works. All right, if you guys need to talk to me, hit me up on Discord.